In this lesson, we're going to learn about systems of equations through graphing. So first, what is a system of equations? So far, you've been dealing with equations, for the most part, just one at a time. Now, a system of equations is a set of two or more equations with the same variables. Now, a system can have quite a few equations, though in this chapter we're just going to be looking at two linear equations at a time. So for example, the types of systems that you'll see might look like this. Here's our first equation, y equals x minus 3. And our second equation could be something like y equals 2x minus 5. Now you'll notice I've written them in slope-intercept form. You might not always see your systems written in slope-intercept form. They could be written in standard form or point-slope form or just a random form. But you'll find it helpful as we go through the lessons to put them in slope-intercept form, at least as we're getting started. Later on you'll see a little bit more with standard form and also a little bit with point-slope form as well. Now, when we're looking at a system of equations, the main thing we're concerned about is the solution to the system. Now, a solution to a system of two linear equations is simply the ordered pair or pairs that satisfy the equations in the system. So when we graph systems of equations, we're looking for the point that the two linear equations share. It's the point where the two lines cross or intersect. Sometimes, as you'll see in just a little bit with our three cases here, sometimes there will be multiple points, sometimes there'll be one, and sometimes there won't be any at all. So for our example, we're going to look back up at the system we wrote in the previous example. Now the solution to this system of equations is the point 2, negative 1. We can check that by, from our first equation, using the point and seeing if we get a true statement. If we get a true statement, then we know that this is a solution for the first equation. We're going to try it then with our second equation. When we put our point in our second equation, if we get a true statement, then we know that this point is also a solution for the second equation. If the point is a solution for both equations, then we know it's a solution for the system. So let's go ahead and verify. So our first equation, y equals x minus 3. 2 is our x-coordinate. Negative 1 is our y-coordinate. Okay, let's simplify. So 2 minus 3, negative 1. Negative 1 does equal negative 1, so we get a true statement. So we know this point is a solution for our first equation. Let's try the second equation. Let's verify. Our second equation was y equals 2x minus 5. Let's put in our point. Well, 2 is our x-coordinate, and negative 1 is our y-coordinate. Let's simplify. 2 times 2 is 4. 4 minus 5 is negative 1, and negative 1 does equal negative 1, so this is also a true statement, and we know that this point is a solution for this equation as well. Since this point is the solution for both equations, we know that this point is the solution to the system of equations. So let's go ahead and take a look at what can happen when we graph a system of two linear equations. Now there are three things that can happen when you're graphing two linear equations. The first thing that can happen is you graph your two lines and they cross or intersect in one place. You could graph your equations, graph the first one, and then you go to graph the second one and you realize, well, it's just the same line. The last thing that can happen is you might graph your first line, and then you go to graph your second line and you see that they are parallel. So when you graph two linear equations in a system, they might cross in one place, they might be exactly the same line and have all the same points in common, or they might be parallel lines and have no points in common. So when we're looking for solutions for each case of these systems of two linear equations, in our first case of intersecting lines, we have one shared point. There's one point that is a solution for both equations. So that is the solution for the system. We have one point that works. We have one solution for the system. And it is exactly where the lines intersect. Now in the case of the same line, okay, you had two equations, you ended up graphing the same line, those two equations are sitting right on top of each other. That means they have every single point on this line in common. And we know that there are infinitely many points on a line because it extends infinitely in both directions. So the solution for this type of system, where you have the same line, we have infinitely many solutions because every single point on the line would work in both equations. Now, in the case of parallel lines, we know that parallel lines will never cross, they will never intersect, so they have no points in common. In this case, we have no solution. So we have a few different vocabulary words that we can use to describe these three cases that happen when we graph a system of two linear equations. Now, a system of two linear equations can be either consistent or can be inconsistent. So a system of equations is consistent when it has at least one ordered pair that satisfies both of the equations. So let's take a look at those three cases again. Now, which set has at least one solution that satisfies both equations? Well, in the case of intersecting lines, it has exactly one. So we could call this system consistent. And on the case of the same line, they have infinitely many solutions, and infinitely many is definitely at least one. So this type is also consistent. Now, a consistent system can be either independent or dependent. If it's independent, it has exactly one solution. If it's dependent, it has an infinite number of solutions. So let's look back at those three cases that we can have in a system of two linear equations. Our case of intersecting lines, there is exactly one solution, and that's just our definition of independence. So this system is consistent and independent. The case of the same line, we have infinitely many solutions, so it is consistent and dependent. Now, an inconsistent system of equations is just a system of equations that has no ordered pair that satisfies both equations. So in other words, an inconsistent system is one that has no solution. So let's look back at our three cases, and we really only have one choice of a type of system for no solution, and that is the case with parallel lines. They do not intersect, they have no points in common, there is no solution, so this system is inconsistent. All right, let's do a few examples. So first we're asked to determine whether each system, each pair of equations here, has no solution, one solution, or infinitely many solutions. So what we're really looking for is which case, intersecting, same line, or parallel lines, are each of these sets of equations. So let's take a look at the first example. Let's find on our graph the equation y equals x minus 4. And that is the one that is down here. Okay, we're taking a look at this one. And we need to find y equals 1/3 x minus 2. And that's just this one right here. So this looks like the case of intersecting lines. And we know intersecting lines only have one solution. And here it is. It's the shared point between both of these equations. So this point here, 3, -1, is the solution for this system. So we have one solution, namely the point 3, -1. Let's take a look at the second example. So we have y equals 1/3 x plus 2. This one here. And y equals 1/3 x minus 2. Well, that's just this one down here. Okay, so we're looking at these two, and they appear to be parallel. And if we look at the equations, we can see, well, they're already in slope-intercept form, and their slope is 1/3 for both of them, so we know that they're parallel. So in the case of parallel lines, we know there is no solution. Since they will not cross, there will be no points in common. Okay, the third example, example C, we're looking at x minus y equals 4. Let's look at this one here. X minus y equals 4, and y equals x minus 4. Well, that's just this one again. Okay, this is the case of same line. And in the case of same line, we know that every single point on the lines will be a solution. And since there are infinitely many points on a line, we know that you will have infinitely many solutions. Okay, the last example, we are looking at x minus y equals 4. That's this one here. And we're looking at -1/3 x plus 4, this one here. Okay, it looks like this is the case of intersecting lines. We now have one solution. It looks like they cross in only one place, right here at the point 6, 2. All right, in our next set of examples, we are going to graph the system of equations, and we're going to determine whether it has no solution, one solution, or infinitely many solutions. If the system has one solution, we're going to point it out. We're going to name it. We're going to say exactly which point it is. So let's take a look at this first set of equations. We have y equals -x, or the opposite of x. So these, and the second one we have y equals 2x. So these are already in slope-intercept form. Now remember, slope-intercept form is y equals mx plus b. So in the first equation, our slope is -1. Remember, when we have no number on the front of x, we know that the coefficient is just automatically 1, because 1 times x is x. So our slope in this case is -1, which if you rewrite a fraction, it's the same as -1 over 1. Our y-intercept, in this case, is 0. So let's graph. Let's graph our y-intercept first, 0. And then we can use our slope to find another point on the line. So our slope, -1 over 1, let's go down 1 and right 1. Now we have 2 points that are on the line. We can graph the line. Let's take a look at that second equation. Our slope, in this case, is 2, which as a fraction can be written 2 over 1. And our y-intercept, again, is 0. So let's graph our y-intercept. Here it is at 0. And we'll use our slope, 2 over 1, up 2 and right 1, to find the next point on the line. We have 2 points. We can graph the line. And this looks like the case of intersecting lines. Where do they intersect? Well, at the origin point here, where both of those lines cross. So we know this system of equation has one solution, namely the point 0, 0, or the origin point. All right, let's take a look at the other set. Now these aren't in slope-intercept form. I think it's easiest to put them in slope-intercept form and then graph using the y-intercept and the slope. Your other option would be to choose a value for x and then find the corresponding y value. Do that twice for each equation. You'll have 2 points on each line, and that way you can graph the lines. So it's up to you whichever method you choose. I like to put it in slope-intercept form first, so that's what I'm going to do. So our first equation, x plus y equals 8. Let's get it in slope-intercept form. So I'm just going to subtract x from both sides, and I end up with y equals the opposite of x, or -x, plus 8. So my slope for this equation is -1 as a fraction, -1 over 1, and my y-intercept is 8. My second equation, let's put that in slope-intercept form. We have x minus y equals 2. Subtract x from both sides. You get the opposite of y equals the opposite of x plus 2. Now, to get rid of this negative sign in front of the y, you can either divide through by -1 or you can multiply through by -1. Either way, they'll get you these same answers. So let's go ahead and divide through by -1. And remember, whatever you do to one side, you have to do to the other. You have to do it to the whole side. So we end up with y equals x minus 2. So our slope, in this case, is +1, or 1 over 1, and our y-intercept is -2. So let's go ahead and graph these equations. So our first equation, our y-intercept was 8. 1, 2, 3, 4, 5, 6, 7, 8. So we're going to start with our y-intercept of 8. And our slope is -1 over 1. So let's go down 1 and right 1. There we have 2 points. Now we can graph our line. All right, our second equation, our y-intercept is -2. Start down here at -2. And our slope is 1, so we're going to go up 1 and right 1. Okay, we'll go ahead and draw our line through our points. And this looks again like the case of intersecting lines. And here's where they intersect. Only in one place. At the point, looks like 1, 2, 3, 4, 5, 1, 2, 3, 5, 3. So this case has one solution, namely the point 5, 3. Now, to determine whether a system of equations has one solution, no solutions, or infinitely many solutions, sometimes you won't even have to graph the equations. You can just play around with the forms of these equations, check out their slopes, and see how many solutions, or if at all, if they have a solution. So let's take a look at, here's an example where we're dealing with the same line. Now these two equations look different, but let's rearrange them and see if they are in fact the same line. So this first one is already in slope-intercept form. The second one is not. I'm going to put the second one in slope-intercept form and see if we do get the same line. So we're starting with 4x minus 2y equals negative 2. Let's subtract 4x on both sides. You end up with negative 2y equals negative 4x minus 2. Now to get rid of this negative 2 on the outside of the y, we're going to go ahead and divide through by negative 2. Divide this whole side by negative 2. We end up with y equals, let's see, negative 4 divided by negative 2 is positive 2. X. Negative 2 divided by negative 2 is positive 1. So here's what our second equation simplifies to. And look at that, it's exactly the same as the first equation. So we're dealing with a case of the same lines. And in the case of same lines, we know that there are infinitely many solutions. So let's take a look at the case with parallel lines. Now, from this form, we can't tell exactly if these lines are parallel. Let's put them into a form where we can look at the slopes and see if we have the same slopes. So if the slopes are the same, the lines are parallel. So let's go ahead and put these into slope-intercept form because I think that's easiest to see the slopes. So let's take a look at this first equation. We have 3x equals y minus 2. Let's go ahead and put this in slope-intercept form. Let's add 2 to both sides. You get 3x plus 2 equals y, or you could rewrite it the other way, y equals 3x plus 2. Let's go ahead and do the same with the second equation. We have 2y equals 6x minus 2. Okay, let's go ahead and simplify down. Let's find our slope-intercept form. So to get rid of this 2, let's divide through by 2. Y equals, well, 6x divided by 2 is 3x, and negative 2 divided by 2 is negative 1. So our first equation in slope-intercept form is this. Our second equation in slope-intercept form is this. And let's take a look. Well, they both have a slope of 3. They have the same slope. That means they're parallel lines. So we know they will never intersect, so there is no solution. Okay, let's take a look at the last case, a case of intersecting lines. So they're already in slope-intercept form for us. Let's take a look and see if they're the same line. Okay, upon examination, you'll see that they're not. Are they parallel? Well, this one has a slope of 3, this one has a slope of negative 1, so they're not parallel. So they must be intersecting lines. That's your only leftover choice. So in the case of intersecting lines, we know that there is only one solution. Okay, naming the solution, you could graph these two equations and see where they intersect, see the point where they cross. That would be your solution. Over the next couple of lessons, we're going to find other ways to find the exact one solution for a system of equations with intersecting lines.